And we're live. Welcome, everyone. Welcome to the PyTorch 2.0 Ask the Engineers live stream series. If you're just joining in, if this is your first part of this series, then this is a live stream where we have experts from the PyTorch team here to talk about all the new capabilities that were announced.
If this is your first
Um,
part of the series, then this is a live
Give
stream
me a
where we
second.
have experts from the PyTorch team here to talk about all the new capabilities that were announced.
I'm hearing echoes. Give me a second while we
Give me
figure
a
it out.
second. Experts from the PyTorch team here to talk about all the new capabilities that were announced.
Did we get rid of it? Okay. Ah, I don't hear any more echoes. Okay, let's go
Did
then.
we get rid of it? Okay.
I,
Ah,
I apologize. I
I
think
don't
we
hear
still
any
have
more
echoes.
echoes.
Sorry for the technical difficulties. We're still figuring out what the echo is from, and I'm gonna figure it out and get back to you. Give me a second while I figure it out. I apologize.
Sorry for the technical difficulties.
Okay. I hope that should have resolved it. I apologize, folks. We are 2 minutes in. I'm sorry for the technical difficulties we were
Okay.
having.
I hope that could have resolved it. I apologize, folks. We are 2 minutes in. I'm sorry for the technical difficulties we were having.
Do do we still hear echoes?
Is it because you are trying to play your sound? So
Yeah. No, I think it's gone. I think yeah, I think we figured it out. Okay, let's start clean. We're 3 minutes in. I'm sorry. Let's start clean. Okay. Welcome, everyone. I'm Shashank, and this is the PyTorch 2.0 Ask the Engineer series. We'll jump right in. If you're new, this is the series where we have experts from the PyTorch team to answer questions about the new capabilities in PyTorch 2.0. The previous recordings are available at pytorch.org/events. Upcoming events are available there, and also the previous ones. And if you want to watch the recordings, they're also available on the YouTube channel. And once again, I apologize for the technical difficulties. So we'll just do a quick round of introductions and get started. Again, I'm Shashank. Junjie and Wanchao, who wants to go next?
I can go next. Hi, I'm Junjie. I'm from the PyTorch distributed team. I work on Tensor Parallelism and 2D Parallel. Next, Wanchao.
Hi everyone, my name is Wanchao. I'm from the PyTorch distributed team at Meta and working on primarily on PyTorch Detensor and work with Junjie together on other stuff too. Yeah, nice to meet you.
Awesome. Okay, welcome. Again, final round of apologies for the technical difficulties. So, distributed tensor. PyTorch has several distributed capabilities, right? We have torch distributed, we have fully sharded data parallel, different paradigms for model parallel, data parallel. How is this different, or what is distributed tensor, and why do we need it with the capabilities that already exist today?
Yeah, I think this story all starts from when we want to explore the area of model parallelism. I think over the years, the industry developed several different model parallelism technologies like tensor parallel, pipeline parallel, and for example, zero style fully sharded data parallel too. So we have been trying to enable the tensor parallel solution in PyTorch natively, and we also want to not only make a sort of a short solution that just only work for data parallel. We look at it from a holistic view, where we see that the currently all of the distributed training technologies, they're actually working on a separate dimension where solutions have been built independently. For example, I think people in the industry love PyTorch DDP, and we recently developed FSDP, and we have like exploring pipeline parallelism too. But when training large models, I think usually people want to actually combine all this technology together. The interoperability of like existing solutions are not actually great and often a bit hard to use. For example, user may want to just like combine data parallel with tensor parallel, data parallel with pipeline parallel, stuff like that. And I think this is become an issue for user. And I think the fundamental reason here is that it lacks a common abstraction to build a bridge between different parallelism strategies. So this is the reason we invent distributed tensor. Is a common abstraction that works and it's useful to use it to express things like data parallel and tensor parallel. And it's a common abstraction for SPMD training.
Yeah. That's awesome. And so you mentioned data parallel and pipeline parallel existing methods, and what would you say are some of the use cases where this would shine specifically, like large scale use cases where this specific new API and functionality would shine?
It's first of all, it's a tensor abstraction, and it really we really are trying to make it work almost like a torch tensor with almost the same capability, so people can actually work on top of it and building parallelism solutions and parallel like strategies based on their custom use case easily. And this will be I think the sort of a fundamental primitive people can play with, and we want it to be a building block, but rather an end-to-end solution. And I think we have tensor parallel as our end-to-end solution already, like as a first use case of this, which we actually build this tensor parallel on top of distributed tensor, and it already enable us to scale up the model training. I think Junjie maybe can talk more about that later.
Yeah, sure. So basically, in the past, as you can see, we have like three different types of model parallelism paradigms. So for tensor parallelism, we focus on within layer model parallel. So we somehow can either shard the tensors across different GPUs. We leverage the NVLink within one host, so that we hope this will speed up the communication across different GPUs. So we want to leverage that for tensor parallelism. And then Detensor actually provide a really good way for us to, in a good way and an abstract way for us to implement tensor parallelism on top of that. And then in terms of unblocking training large model, we observed that on a VIT 120 billion model, that on that size, after applying tensor parallelism, we can train the model versus if you only apply data parallel, it is not doable. Yeah.
Is it just a user ease of use abstraction layer on top of existing things that are available, or are there new capabilities outside of the API that are available in this news feature? In other words, is it just a new, easy to use API for existing capabilities, or are there new capabilities?
I think.
I think yeah.
Sorry, go ahead.
I just want to mention that we provide a flexible tensor sharding approach natively in PyTorch. This is something not existing before
Oh, okay.
before Tensor Parallel and the Detensor. Yeah.
Got it.
Right.
And you mentioned Detensor a couple of times. So this is the new data type, if you will, that parallels tensor, torch.tensor, right? What are the, I guess, fundamental difference between Detensor and tensor? Would all the other capabilities be mirrored on Detensor and it will seamlessly work in a distributed fashion, or are there limitations? How would you compare those two?
Yeah, so you can think of Detensor more like offer a uniform way to do distributed training, and it really should work as a tensor, and that's or one of our go-to. We want to make sure Detensor really look like a tensor, and it works on a set of devices instead of a single device. And what Detensor offer here is that Detensor offer a way for you to distribute your large tensors across devices easily, and it also has several layout that we actually can describe the data distributions and computation across hosts. So, for example, we have like a concept in Detensor, we call it device mesh, which is abstraction that could actually help describe the global view and topology of the devices within a cluster. For example, you have like two hosts, and each host has several devices. This is easily construct set up some communicator, like we set up through the device mesh by just calling a very simple API. And Detensor itself has different style of placement where we can shard a tensor across tensor dimension across devices. We can replicate the whole tensor across devices, and we can also sort of having produce a partial result that actually partition the values across devices. So basically, in the era of distributed training, you often encounter different kind of distribution strategies, and the ability to transform between one placement type to the other placement type is something unique that distributed tensor offers. And with these three placement type, we're able to run the distributed computation really like a torch.tensor, where user don't need to be aware of like it's a different data structure when training in SPMD manner.
That's really cool that the user doesn't need to. So user only specifies the distributed tensor types and use the Detensor, and under the hood you'll take care of how it's sharded or replicated, and they'll just continue to use it as they would use a regular torch tensor. And in terms of the list of capabilities in PyTorch that would out of the box work with this, like would all the linear algebra, would all the other capabilities just work out of the box, or are there limited set of capabilities that would work?
Actually, a very good question. So basically, we started building this in the middle of last year, and we are releasing it as a prototype release in the upcoming 2.0 release. And right now the state of distributed tensor is that we would like to support all kind of tensor operations that PyTorch torch.tensor offers. But we are still building it up by like a lot of, for example, a lot of computation on linear algebra libraries may not be supported yet, but we do support basic modes, wheel operations, like all the pointwise operators are supported right now, and yeah, it may take some time for us to build the whole operator set, but I think we sort of figuring out a way for us to enable the op coverage to reach to 100% finally. Yeah, but it's a in progress effort right now. Yeah.
Yeah, that's like the ultimate goal of Detensor, to support the full breadth of PyTorch functionality.
Yeah.
There's a question. If I'll would you like to take it now, or did you have something to finish up before we take a question?
I just have one point to add here, to add
Yeah.
on top of one point. Although right now we're still see some gap there, until we reach the 100% op coverage. But in the past year, we specifically focus on transformer-based model. So for our communities, we know transformer model are heavily used by PyTorch users. So I would say, like, for most these ops are supported for transformers. So we highly want the community to try it out. If you have any specific requirement, just let us know, so then we can know your know community's requirement there.
Right.
Yeah.
Right. And a quick reminder to all the viewers: this is a Q&A series, so it's less of presentation, more about answering your questions. So please put in your questions. And you just heard we are inviting requests for what is important to you, so they can prioritize support for those capabilities, with transformers being the initial one. There's one question in the chat. This is it's a question I had to actually. How does Detensor integrate with Torch Dynamo? Or a little more broadly, how does it work with the new capabilities in PyTorch 2.0, which is PyTorch compile, right? So how does it play well with the new compiler technology that's in PyTorch 2.0?
Yeah, that's a very good question, and this is actually something we are exploring. So the approach that we are seeing is that Torch Dynamo is an approach that allow PyTorch program to easily capture the graph and lower them into some backend compiler to speed up the execution. And we think that Torch Dynamo, AOD Autograd, and Torch Inductor, all these technology that shines the PyTorch 2.0 are really amazing, and we want to leverage the whole compiler stack to speed up the training, especially Detensor itself would benefit a lot on using the compiler technology to speed up the execution. Yeah. So in terms of how we gonna do it, I think the current approach is that we will actually capture the local model graph first, using Torch Dynamo and AOD Autograph. The ideal state we want is that we would be able to capture the full train step of your model training, and that will be a full graph, and that graph with no with no graph break right now. Like, if we get the full graph, we will be able to annotate the Detensor placement types onto that graph, and to sort of express different parallelism strategies. For example, part of your graph you want to do data parallel training, so data parallel training will just annotate that part of the graph with the parameters by like replicating all the parameters. And part of the graph you want fully sharded data parallel, we will just shard all that layer within that graph, and then we will use Detensor sharding propagation path to actually expand the whole graph with all the shardings we want. And once we get a full graph with shardings, we will materialize it with distributed tensor for the runtime execution, and then we will actually at this time it's a local model and getting transformed into a distributed model already. Then we will apply several optimization that could able to speed up the training. For example, a common theme that DTP training is really great is that is able to combine a lot of the OR-reduce operations into one big OR-reduce, and it is able to delay the OR-reduce and fire that OR-reduce at a certain time. And with that in mind, with the graph we have, with the Detensor sharding tabs we have, we also will generate the OR-reduce for the distributed graph, and then we are actually able to manipulate the graph to be able to do such kind of a fusion for OR-reduce. And this is very similar to fully sharded data parallel 2 or other tensor parallel pattern. We are able to, once we get the graph, we are able to identify some of the opportunities that people want to speed it up, and all this optimization opportunity can be explored there. This is something on my mind, and also on we have been having very frequent discussion recently about how this should work within our team too. But it's something we are still exploring and haven't actually fully converged into a solution yet. And I think once we actually figure out a solution and we actually work towards that solution onto, for example, another prototype release, we will share this with all the people here, and hopefully, I think we can get more feedback about the approach that we are doing. Yeah.
Awesome. And so basically, I heard that you are in your API or under the hood are already performing some graph optimizations, right, to some extent, and then Torch Compile is also responsible for it. But how they would all work together is sort of an ongoing discussion within the team on how to support it. You mentioned data parallel, and this is distributed tensor is tensor parallel. I guess, is that what you mean by 2D parallelism? And how do you think about how do we think about those two together?
Yeah, so I want to mention that Detensor is more like a fundamental primitive that describe data distribution and computation. So ideally, it could represent almost every parallelism patterns. That's why I think data parallel can also be described by Detensor too.
That's interesting.
Yeah, and also like tensor parallel is another thing, right? Like 2D parallel, basically what we are introducing here is that we are introducing tensor parallel combination with data parallel, and if we can use a uniform data abstraction to represent such a thing, that will be very easy to compose with each other and also be able to do a joint optimization in some sense. So that's why for 2D parallel, for data parallel, it's all should be able to represent by Detensor. And it's just that when combining, for example, when just purely implementing data parallel or Detensor, using Detensor, right, is gonna be pretty slow at this moment, purely because when we are doing tensor operations, we are only seeing that op alone, and we don't see all the other ops adjacent to it. And one of the biggest DDP improvement is that it's able to see the whole model, so that it actually could group all these collectives together and then fuse them together. That's what I think the Torch Dynamo integration and the Torch Compile integration is needed, because once we get these Torch Compile and Torch Dynamo, we have the full graph visibility. We could be able to do this optimization on top of the graph level instead of on the tensor operation level.
Got it. And I know you do have a code example demo to walk through, but before that, there's a follow-up question from the earlier question about integration with Torch Dynamo. Will it be possible to implement sequence parallelism coming from the latest Megatron LM version with Detensor?
Yeah, actually I saw this question, so I was about to answer that. So to answer, the short answer to this question is that yes, we just enabled it like maybe 1 or 2 weeks ago. But the caveat here is that it is not well perf optimized yet. So the original paper from Megatron LM is that they had some bunch of activation memory saving techniques there, so they can save the activation memories. Currently, we don't have that feature ready yet, but if you want to just try the like a vanilla sequence parallel, yes, I would say you can use that by using Detensor. Yeah, we even have a example for that. Yeah.
Where can we? Is it public, Junjie, to share the example, or is it?
Yes. I can maybe I can find the link and then share with you, and then we can share with the community.
Yeah,
Yeah.
yeah. If you find it during the stream, we'll just share it in the stream. If not, we'll just put it in the comments later on. Awesome.
Sure. Let me get the link for you right now. Yeah.
Okay. So I think now it might be a good time to take a closer look at the API. Unless you have other concepts to cover, Wanchao and Junji. If not, then we can take a look at the code example you have where you can walk through the API. Is now a good time to transition? Okay. Okay, let's do it. You're muted, Wanchao.
Okay. So thanks. Yeah. Okay. So let's walk through some of the API examples that we actually have here. So Detensor will be prototype release in 2.0. So we can actually try it right now in the by using the NetBeat version. And this is a collab example. So we need to, first of all, we need to install the PyTorch nightly in order for us to try out Detensor. And also we need to probably import some of the testing functionality that we have, because since we switched to multi-processing, it's really hard to run a multi-processing job in a Jupyter notebook or a Colab notebook. So so you can probably easily do it in a Python file, but within that notebook, we need to have some hacks. So we actually developed some of the testing util for us to spawn multiple thread and mimic or process group abstraction to set up the communicator there. Yeah, this is some util that just enable distributed computation in a notebook. Okay, so let's see what Detensor we are offering right now. So we're living inside torch.distributed_tensor because we're a prototype release. It's not in a public folder yet, but some functionality you can already try it out. So you can basically some necessary import. We import Detensor, US mesh, and all the placement that we have. So a native question is that how we could shard a big tensor across ranks. So this could just be achieved by say we set up the communicator, then we somewhere there's a big tensor. It can be either on meta device or it can be on just like a normal torsion tensor, but it's really big. And then we want to call this distributed tensor API, where we actually takes in a mesh and the placement. Note that the placement length need to match the number of dimension of that mesh. For example, here is a 1D mesh where it only have like one dimensional list. So we only have one item in this placement. So this basically means we want to shard that big tensor on the device mesh with shard placement, where we're sharding on tensor dimension 0. So if you see after just a simple call distribute tensor, we are able to get like this global detensor here. And if we see the detensor global shape is still the same shape as the original torch tensor, but its local shape already getting sharded and splitted across ranks. So the local shape all become divided by 4 here. So another placement that Detensor offers is that we could be able to also replicate a big tensor across ranks. You may wonder why we need to do that, but I think that's simply because for data parallel, all parameters are replicated, and we need to sort of in some cases not only consider sharding but also consider replicating too. So, for example, to replicate a tensor is very similar to shard a tensor. It's just that the placement tab now become a replicate object, and then after the replication, the Detensor global size will be the same as the big tensor, and the local size will also be the same as the big tensor because we're replicating it across devices. So with another very beneficial part for Detensor is that normally people want to do sharding, but sometimes there will be a complex sharding strategies. Say we want to shard a big tensor in a subset of devices and then replicate all the shards in another set of devices, right? So this can be easily achieved too by actually creating a 2D device mesh where we actually create the device mesh by just passing a torch tensor as a sort of like a list of device IDs, and then we can reshape it to the way that we want. For example, here we want a 2D mesh where for the 0 dimension of the mesh, we want it to be a host dimension. For the first dimension of the mesh, we want it to be the devices within that host, the device dimension. So after creating that device mesh, and we got a single big tensor, and we can just simply specify the sharding, the placement to be replicate on the first dimension of the mesh, and then shard on the second dimension of the mesh. So, and then we again pass this to DistributedTensor. It will actually correctly distribute the big tensor into the corresponding format we want. For example, we can see that right now the local shape is only divided by 2, and that means like we're sharding on 2 devices and then replicating on the other 2. Yeah. So how do we? A common question here is how do we? We can sort of do distribute tensor to shard and replicate a tensor, right? But what if I have a local tensor on each of my rank? I just want to create a detensor from that. I don't want to eagerly do the sharding or eagerly do the replicating, right? So we offer API for us to interact between torch.tensor and the detensor. These two API are from local and to local. From local, we are actually converting torch.tensor to a detensor in SDMD fashion. Then we can call, when necessary, we can call to local, where we convert that detensor to a torch.tensor in each rank in the SBMD fashion. And note that both from local and to local are differentiable, so that we can actually just let part of your model be detensor, but not the whole model. So this is an example of the usage of using from local and to local. We can see that we had a local tensor on each rank. Word size is 4, for example, and then we specify a shard placement. This shard placement means we are sharding on tensor dimension 0 for that detensor. When we call from local, immediately we'll get a detensor that is actually having a larger shape than your local tensor on each rank. So that is actually just taking that local tensor and form a bigger detensor automatically. And then we can, after that, whenever we want, we can actually call the detensor.toLocal, and we can access the local torch.tensor by calling, for example, the shape of that local tensor. Yeah. Another capability is that because in Detensor we offer that kind of placement, right? For example, you see that we have shard, we have replicate, and we have partial. most likely the user-facing one will be shard and replicate. And how do we transform from one type of detensor to the other type of detensor? This is critical because a lot of times you are having two detensors and they are not actually aligned with each other. So we want to do the transformation before we really run the compute. This is an example. For example, we can create row-wise sharding tensor by specify we're sharding on dimension 0 of the tensor. Then we call from local, we form a row-wise tensor. And then once we form the row-wise tensor, we can do the transformation by calling an API called redistribute. Let's see, say the redistribute API takes a mesh, which is a device we want to redistribute on, and a new placement. For example, we want to make this row-wise detensor convert into a column-wise detensor. We can just call redistribute, and it will automatically convert it to replicate. For example, here we can have the global shape are still the same, but the local one right now becomes 32.2 instead of like 8.8, right? So this is some of the transformation we did here. And also you can also have, for example, if you want to actually replicating the tensor from the shard, you can also call redistribute and pass a replicate placement. And that will actually trigger an all gather operation where we can all gather all of the shard on all devices and form a replicated tensor. Yeah, this is just by simply we can call redistribute and you can get different form of detensor be converted to and from. Yeah, that's basically example usage of detensor. We are actually furnishing up the different APIs. In the meanwhile, we are actually adding something like torch.distributed.zeros for you to directly construct a zero tensor on set of devices. And we are actually like improving the API tool. So welcome any suggestions to the API. Feel free to directly submit an issue that or even we welcome contribution too. We have a lot of things here. So yeah, contributions are welcomed. And then I think because we have like a tensor parallel built on top of Detensor, I think Junjie can walk through the tensor parallel example that built on top of Detensor, how we use it to easily parallel a model.
Yeah, sure. So next I will talk about tensor parallel example here. So since we built this on top of Detensor, as you can see, it should be super simple. So first, we define a toy model here. The reason we define the model like this is because the original Megatron LM style are like using two linear MLP together. So we just stack them together to kind of mimic what Megatron LM is doing. We also have this high level API in Torch distribute. So can you still stay scroll up a little bit? Yeah, so we have this high level API distributed tensor parallel. So user can just call this parallelize module to basically annotate their model so that after that we will handle everything under the hood. And then we have another concept called parallel style. So basically you can have a column-wise parallel or row-wise parallel, or for this case we're using pairwise parallel, which is that because with two linear together, we want to use what Megatron is doing. Basically, you first have a column-wise sharding, and then you have another row-wise in the second layer. So then you don't need to do any collection until the very end. Yes, so that's basically it. Do you mind scrolling down a little bit? Yeah, next we will basically go through a real example here. As you can see, do you mind scrolling down a little bit more? Yeah, so here we're running this in SPMD style. So same thing as Detensor. First, we need to create this device mesh. So since this is a 1D parallel case, so then you only need to create a very simple device mesh here. If it's 2D or 3D, then you have to like change the device mesh accordingly. And then after you have the model, you just need to have a one line call here, like model, parallelized module model. You pass in the device mesh and then the pairwise parallel style, then that's it. And then the rest are the same. You can do the forward and backward optimization. Same thing. Same thing. As what you are doing for a normal tensor module. Yeah.
That looks pretty straightforward actually. Once you define everything, you just wrap it with the parallelize
Right.
what's that parallelize module, and then you don't have to worry about rest of the training
Right.
loop. Thing is just
Right.
how you used to writing it. That's
Right.
pretty cool. I
Right.
think, yeah, in my opinion, like the user interface is the main thing. If you nail the user interface, then adoption becomes much more easy. There are a couple
Yeah.
of questions there. Do we want to try and take them? And if you have other concepts, we can
Uh,
cover after.
Before we go
Other,
to questions, let's quickly mention one more thing here.
one more
Do
thing.
you want to, if you scroll down here in the very end, so here we didn't provide a real like 2D parallel example here is because FS fully sharded data parallel FSDP can only run GPU. So we attach a link here. If user are interested, please go here. And another thing is that with PyPy parallelism. So last year during the PyTorch conference, we've got feedback from community asking us for say, hey, when do you guys have the integration of like pipeline parallelism with tensor parallelism? Now we have that today, so we also provide a link here. So if the communities are interested, please check out
Junji,
the
for someone who's not familiar, what is PyPy and how is it different?
Yeah, pipeline parallelism. If we can go back to the slide, maybe. So that's another concept I think which also being brought in PyTorch 2.0. Um, is that it kind of like split a large model into several stage. So it's one of the parallelism paradigms. So we have data parallel and then tensor parallel and then pipeline parallel. So this one is first the chunk the model into like a very uh very like a coarse grain level. So you chunk the model into several stage, and then we will do data parallel and then model parallel on top of that. And then this is explicitly asked from the community, so people are very looking forward. So that's why I mentioned here.
Yeah, we have coverage on all areas now, right? And the PyPy package, it says, is prototype stage. And are you saying the distributed tensor is also in the prototype stage today? Or um, let me go back to because you have call to action here. So let me go back to the Jupyter notebook.
Yeah, so basically both Tensor Parallel and Detensor is in early stage of development. We are releasing prototype with PyTorch 2.0. So yeah, feel free to actually try it out right now with the nightly or with the upcoming 2.0 release. So if you actually meet some blockers when actually playing it around with different different patterns, feel free to file a GitHub issue or even open a PR to contribute. We really appreciate community contribution here. Yeah.
Okay. Yeah, two ways to contribute, right? One is to just tell if something's broken, and the second is actually to contribute. Yeah, it doesn't, I guess, people fear contribution because they feel it's a lot of work, but even raising an issue is a way to contribute to open source, right? You're making issues aware. So both effective ways to contribute. Let's do the questions. A couple of questions came in a while ago. So one of the questions is there a plan to co-optimize with data processing, or is there a question for inductor and torch data? Like, how do they work together, I guess?
Data processing, I think it's a torch data field. Basically, I'm referring to this as like when you load the data from data loader, you want to have some data pre-processing before feeding into the model. I think this is something maybe the inductor and the torch data need to figure out a plan on how to do data processing. In terms of how do we do distributed data processing optimization.
Right, I think that's what they're referring to. How do you use this capability in the context of data processing before model training?
Yeah, so the current thing I am having is that right now data loader produce directly like a torch tensor on each rank. We could actually let the data loader directly output the Detensor, and then we actually do some optimization if the data processing requires some distributed computations. This is something not yet started.
Yeah.
It's just something on top of my mind.
I think this relates to the question I asked you about, will the whole set of PyTorch capability be supported? And you said the focus today is transformers, which makes sense, right? Today you're focusing on the model training part of it. At some point in the fullness of time, other capabilities of PyTorch would be supported, in which case you can easily use it for other parts of the pipeline, which is data loading and data pre-processing. Awesome. The other question was a follow-up on Dynamo integration. If we use the Detensor API to shard a tensor and then try to capture the module using torch.compile, does it error or break the graph when Detensor shows up? Yeah, I guess how the compiler behaves in the presence of.
Yeah, that's a good question. So we originally think we should actually use Detensor, do the sharding, and then Dynamo then capture the one that after Detensor sharded. So there's some fundamental issue that I don't think it's easy to solve, is that Dynamo itself is a graph capturing tool. It captures up all your Python code, but it's not easy to capture into the C++ code. And because Detensor is working on the dispatcher level, there's actually something happens between the Python. Although Detensor is a Python abstraction, but it is actually using torch dispatch. So it's actually under the dispatcher level, which bakes into some C++ code implicitly. So Dynamo could not easily capture the torch dispatch functionalities as of today. And so in terms of whether we want to use Detensor API to shard a tensor and then try to capture the module, what we are exploring is that we want to capture the module first, and then use Detensor to shard the module afterwards. That's what we are exploring. Yeah.
Awesome. Yeah, I think that
and
covers all the open questions. Go ahead.
Yeah, and also want to mention again about, does it error out or break the graph when Detensor shows up? I think it will. I don't know. I didn't try it, but I think Dynamo will treat the Detensor as a torch tensor, and then it doesn't goes into the details about it. It just treated as a torch tensor, and then it will just generate a torch tensor graph maybe, or it will produce a graph break. I don't think it will error out. I think Dynamo would be able to just break the graph gracefully. Yeah.
Okay. It's in the night. Please go try it out. Right.
Yeah.
All right. So those were all the open questions, and again, we have a few more minutes, so feel free to ask any last minute questions if you have. And we'll close after that. But before, I think you already mentioned it, but did you want to touch upon the future or direction of these two? Of course, GA, I mean, general release is next in the plan, but did you want to talk about where this is heading so you can solicit feedback from the community?
Yeah. For Detensor, I think we are trying to build up a lot of stuff and trying to for 2.0 we are releasing prototype, but we hope in 1 or 2 releases, maybe in 2.1 or even 2.2, we want to do a beta release that could actually open it up for the entire public, and then we are also, I think TP, maybe Junjie can talk about the TP and 2D parallel plans too. Yeah.
Oh yeah. So I think for 2.0 we also still keep TP as a prototype feature there. So down the road, I think there are two directions we want to go. One thing is that as we mentioned here, we will integrate with more parallel paradigm like data parallel or even DDP and even 3D parallel. So then we can see how that will help with our model engineers to scale up their model training. And then another direction is that we will try to since the Detensor is evolving and then support more models, and then we can see how we can explore more tensor parallelism for other type of model, not just transformer model. And also after we have figured out how compiler and 2.0 work with Detensor, then we can think about how we can use how we can apply compiler technique together with tensor parallelism. So one example is that, okay, if you know the global view of the graph, then you can do some overlapping, right? Currently, we have the tensor parallelism in eager mode, so it kind of block the critical path somehow. It's synchronized, right? Like if you have a collective, then the model path has to wait there until the collective to be finished. But somehow, if we have the global view of the model graph, then you can overlap the communication and then data calculation. I mean computation, right? So then you can improve the performance there. So that's the next thing I think TP need to think about more. Yeah.
Awesome. I have a question, and let me ask it, and you decide if you want to answer it. At an earlier live stream, we had a session about backend integration. So basically, the APIs that we expose for other hardware vendors and other even potentially like library like vendors who can integrate with our new graph system, right? New compiler system, either through inductor or just interfacing with AOT AutoGrad. And well, the question is, if a new vendor wants to integrate the backend, like how would they be able to work with it you said, I know you said it works on GPUs today only, right? But if potentially someone were to add support for alternate hardware, is there an easy path to that? Or and forgive me if this is like an out there question, I'm just curious.
I think that the only limitation is not coming from TP or Detensor, because Detensor obviously work both on CPU and GPU, and maybe down the road maybe also on TPU. But the limitation comes from like what data parallel we integrate. So we choose FSDP last year, and the FSDP only work on GPU. But down the road, if we integrate with, let's say, DDP and PP, then that shouldn't be a problem there. Yeah, that is my.
Okay, just to call out, there are other hardware options too, like Intel has Habana Gaudi accelerator, AWS has Trainium and Inferential. Where now I guess the ecosystem is just growing of hardware options out there.
So to add on Junjie's point, so it's not because FSDP, I mean FSDP obviously only works on GPU, but it's I think the fundamental reason is that FSDP utilizes CUDA stream a lot in terms of its own development, and also there's this like some collective operations that is only available on Nickel, but not available on for example, other backends like CPU and glue backend for CPU, right? Yeah, so I would say in terms of like supporting different backend, I think if different backend want to actually implement their implementation by having their own sort of like extension of the process group that works. For example, they can implement reduce scatter by themselves, and they just use the process group abstraction. It may help just like unify the experience. And also for like other things like for example, if we do like this reduce scatter and all gather, and then we also need to maybe the backend need to figure out the CUDA stream, how would the CUDA stream gonna be device agnostic. I think we can figure out a way to for different backend to hook up into the distributed training system. One big benefit I would say is that a lot of backend want to do distributed training, and we have this process group abstraction that backend could extend, or either for example, we have MPI backend, we have glue backend that is in PyTorch distributed right now, and they are sort of limited because there's not too much use case. We didn't actually implement with, for example, reduce scatter only available on process group Nico, but not glue, not MPI. And this is something probably we can do it. It's just that no one really, we don't really have a concrete use case there.
Yeah, but just to be clear, like I guess what we're trying to say is that it is extensible. So if some like other like people they want to try their backend, they can. It's doable. Yeah.
Okay.
Yeah, we welcome collaboration on this. Actually, we are actually happy that the different backends can integrate with process group abstractions. Yeah.
Okay. Yeah. That I think that's the gist of it. Is it's possible, but as far as your priorities are concerned, your scope is smaller now because you're looking to have the core functionality go general availability, but other backend providers could integrate, and there isn't like a real reason why it shouldn't work. Okay. We don't have any open questions. I guess we could just wrap up before we discuss call to action. Go try it out in Nightly, right? This capability is available now. And there's another question about making the notebook available. Is it already available that we can share, or if not,
I think we can share it.
Okay. If what we'll do is, we'll just share it in the comment section of the YouTube and LinkedIn as well. Those are the two places we have people watching from, so we'll just share it there. It'll be available to you to test it out, and I shared a couple of other links, which are the Megatron LM link that's part of the, I guess, GitHub repository itself of PyTorch. And anything else did we want to cover before we wrap up? Junjie, Wanchao, any last closing thoughts? No. Okay. No, this was a lot of information. Thank you. I think it was it's new stuff, which is always exciting, and we had some good questions, and we covered all of it. So again, call to action, go try it out. It's in the Nightlies, and the other call to action that I will talk about is about the series in general. This is an ongoing series. We are covering. We've covered a lot of new capabilities: Torch Dynamo, Torch Inductor, Torch Data, a lot of different capabilities in the past. So go check out the recordings on YouTube, PyTorch YouTube channel, and we have many more coming, and those will be linked out of the events page on the PyTorch website. So go check it out. With that, I want to thank you all for attending and spending your time with us, and apologies again for the initial 2 minutes of technical difficulties there. Happens to, I guess, all of us. And Shashank signing out, and see you in the next stream. Bye.
Bye. Thanks.
Thank you. Bye.